Welcome back. In this video, we are going to solve problem 10-75 that is taken from chapter number 10, Strain Transformation, and book name is Mechanics of Material by R.C. Hibbeler, 9th edition. And the topic that we are covering is theory of failure. Now, statement is the component of plane stress at a critical point on A36 steel shell are shown. Determine if failure yielding has occurred on the basis of maximum shear stress theory. So you can see this is the state of stress, plane state of stress, because there is no stress in z direction, so we take this as plane stress problem. So stress on this phase is 70 megapascal. On top phase, this is normal loading, which is 60 megapascal, and this is shear stress, which is 40 megapascal. So let's start with the solution. So what we are going to do is that we will take this x, the direction is positive axis, and this direction is taken as negative axis. And you can see this surface or this edge is perpendicular to this x-axis, or this x-axis is perpendicular to this. So the stress that is acting over it will be represented as sigma xx. So I will write this as sigma x. Similarly, in the y direction, we know that this is sigma y, and you can see that this is the plane which is perpendicular to the y-axis, and here the shear stress occur in the x direction, so we will call it tau of xy. So I can write it that this is tau of xy. So again, here I will write sigma xx is 70 megapascal, where sigma y is minus 60 megapascal, because you can see in the figure that this is compressive, and you have tau of xy, which is 40 megapascal. Why this is positive? So you can see this is tau of xy, this one. Why? Because you can see this is the plane that is perpendicular to the x-axis, and here this shear stress act in the direction of y, positive y. So we will call this tau of xy is 40 megapascal. Okay, now we have all these values, so we know that principal, we will first find principal stresses. So principal stresses sigma 1 and sigma 2 can be obtained by using this equation, that is equal to sigma average plus minus r. Now what is sigma average? So sigma average is equal to sigma xx plus sigma yy divided by 2. So you have value, this is 70 plus minus 60 divided by 2. So I have calculator. So 70 minus 60 divided by 2 is 5. So sigma average is 5 megapascal. And what is r? So I can write it that sigma r is equal to sigma xx minus sigma yy divided by 2 whole square plus tau of xy whole square, and all these values are in square root. Okay, so just put the value. We have this r is sigma x is 70 minus 60 divided by 2 whole square plus tau of xy is 40 whole square under the root. So let's calculate that. I will take 70 plus 60 divided by 2 is 65. So answer square plus 40 square under the root of this answer will give you 76.321 megapascal. Now we know that we have sigma 1 is equal to sigma average plus r, while sigma 2 is equal to sigma average minus r. So sigma average is 5 plus 76.321, while sigma 2 is equal to 5 minus 76.321. We will calculate them. 5 plus answer is sigma 1 is equal to 81.32 megapascal, while this sigma 2 is equal to 5 minus 76.321, and that is equal to minus 71.32 megapascal. Okay, now you have both these 70 sigma 1 and sigma 2. So what you are going to do is that if you draw them on a Mohr circle, so let this is on Mohr circle, you have this as sigma and this is shear stress. Okay, so on this x-axis there is no shear stress, and this is known as principal plane, and this principal stresses always acts on principal plane. So sigma 1 is positive and sigma 2 is negative. So I will write both sigma 1 and sigma 2 have opposite signs. So if I draw it on this principal axis, so let's say for example this is sigma 1, which is equal to 81.32 megapascal, and this is sigma 2, which is equal to minus 71.32 megapascal. So if I draw a Mohr circle in between these 2 points, so it will be like that. it will be a pure circle. But here I do not have any tools to make this, so that's why. So this is the pure circle, and at this point you have sigma 3 is equal to 0. So Mohr circle between sigma 1 and sigma 3 will be like this, while sigma 2 and sigma 3 will be like this. So you can see here that the maximum shear stress will be this one, which will be, we can write it as maximum shear stress. So we'll find this maximum shear stress. So maximum shear stress, here you can see this is equal, this is the radius of circle, this is also radius of circle. So you can see this distance divided by 2 will give you the radius. Clear? And how we'll find this? This will be equal to sigma 1, absolute value of sigma 1 minus sigma 2 divided by 2. So put the values. Sigma 1 is 81.32 minus 71.32 divided by 2. So I will get the maximum shear stress will be equal to 81.32 plus 71.32 is 152.64 divided by 2, and that is equal to, if I divide it by 2, so it will be equal to 76.32 megapascal. Now we have this value of maximum shear stress. So according to maximum shear stress theory, which is also known as Tresca criteria. So if sigma 1 and sigma 2 have both opposite signs, so maximum shear stress, which is equal to this term x, which was equal to sigma 1 minus sigma 2 divided by 2, it should be less or equal to, sigma yield divided by 2. And why? Because sigma yield divided by 2 is equal to maximum shear stress in a tensile uniaxial tension test. So our shear stress should be less than sigma yield divided by 2. Now the value which we have calculated on the left side is 76.32 megapascal, and we do not know sigma y for A36 steel. So what we are going to do is that we will go to the end of the book, and in that you have to go to the average mechanical property table. So here you can see A36 has yield strength, tensile yield strength is 250 megapascal. So I will write it as 250 megapascal. So sigma yield is this one. So sigma yield divided by 2 will be equal to 250 divided by 2, which is 125 megapascal. Here, and you can see this is less than 125 megapascal, as I will write it as 76.32 megapascal is less than 125 megapascal. So based on this result, I will write the conclusion. Based on this result, the steel shall not yield according to maximum shear stress theory, which is also known as Tresca criteria, or we can also call as MSS, maximum shear stress. And this is the answer of this question. So this was all about this problem 10-75. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 10-76 that is taken from chapter number 10, Strain Transformation, and book name is Mechanics of Material by R.C. Hibbler, 9th edition. And the topic that we are covering is theories of failure. So statement is the component of plane stress at a critical point on A36 steel shell are shown. Determine if failure yielding has occurred on the basis of maximum distortion energy theory. So you can see this is plane state of stress that is given over here. In x direction, the stress is 70 megapascal. In y direction, the stress is 60 megapascal, and that is compressive, and the shear stress is 40 megapascal. So what if I take this axis is x-axis, and along vertical we have y-axis. So from this state of stress we can write sigma x is 70 megapascal, sigma y, which is given as minus 60 megapascal, and this tau of xy is equal to 40 megapascal. Why it is positive? Because you can see it is acting on x plane, clear, and the shear stress is in positive y direction. That is why it is positive. So we have this for state of condition. So from this I will write, from this we will find sigma 1 and sigma 2. What are these? These are known as principal stresses, and principal stresses are maximum stresses that are acting on the element. And for finding this principal stresses, we have this formula which is equal to sigma average plus minus r, or you can also write it as sigma average is sigma x plus sigma y divided by 2 plus minus under the root r is equal to sigma x minus sigma y divided by 2 whole square plus tau of xy whole square. Now we will put the values over here. Sigma x is 70 plus minus 60 divided by 2 plus minus under the root 70 minus 60 divided by 2 whole square plus tau of xy is 40 square. Okay, so we can write sigma 1 comma 2 is equal to, I have calculator, so 70 minus 60 divided by 2 is equal to 70 minus 60 is 10, so 10 divided by 2 is 5, so this will be 5 plus minus the second term which is under the square root, so 70 plus 60 divided by 2, 65 square plus 40 square, and if we take the under root of this answer, so it is 76.321, and the unit will be in megapascal. Okay, now what if I want to find sigma 1? So sigma 1 will be equal to 5 plus 76.32, and that will be equal to 76.32 plus 5 is 81.32 megapascal. So I can write sigma 1 is 81.32 megapascal. Now we'll find this sigma 2, and we know that sigma 2 will be equal to this 5 minus 76.321, and when you calculate 5 minus 76.321, that is equal to minus 71.32 megapascal. Okay, so again sigma 2 is minus 71.32 megapascal. Now you have this both sigma 1 and sigma 2. So what we are going to do is that for maximum, we have to check that whether maximum, according to maximum distortion energy, it will yield or not. So for maximum distortion energy theory, if your sigma 1 square plus sigma 2 square minus sigma 1 into sigma 2, that is less than sigma yield square, so it will not yield. Under this condition, it will not yield. Okay, so we will put the value sigma 1 is 81.32 whole square plus sigma 2 is minus 71.32 whole square minus sigma 1 is 81.32 and sigma 2 is minus 71.32, and it should be less than sigma yield square. Okay, so what we are going to do is that I will move this calculator toward this. So here you can see I have 81.32 square plus this minus 71.32 whole square minus 81.32 multiplied by minus 71.32, and we will close the bracket. So it will be equal to 17, I will round it off, 17500 megapascal, and that should be less than sigma yield square. Okay, now we have been given that this material is A36 steel. So for A36, now for A36 steel, we will find sigma y from average mechanical property table that is given at the end of this book. So let's move and find this sigma y. So I will go to the book. Okay, I don't have at this stage, so I will open this book, and here you can see you have this in front of you, that this is A36, so it's already highlighted. I did it for the previous problem. So 250 megapascal, the unit will be 250 megapascal. So again we will move towards sigma is 250 megapascal, and from this, if I want to find sigma square, sigma y square, so what I will do is that 250 square will give you 62500. Okay, and this will be here. I have to remove this unit because it will be the square. Okay, now you can see that if you put the sigma y value from this, if you want to do it. So 77500, you can see that is less than 62,500. So this equation which is holding correct. So it means that I will write the conclusion. So based on this results, the steel shell does not yield according to maximum distortion energy theory, or it is also known as von Mises theory or von Mises criteria. So this was all about this problem 10-76. We can compare it with our previous problem that we did the same thing for maximum shear stress theory. I hope you have enjoyed both these videos, and those who are new to my channel, then I will request them to subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you so much for your kind support. Welcome back. In this video, we are going to solve problem 10-80 that is taken from chapter number 10, Strain Transformation, and book name is Mechanics of Material by R.C. Hibbeler, 9th edition. And the topic that we are covering is theories of failure. So statement is the yield stress for a uranium alloy is 160 megapascal if machine part is made up of this material and a critical point in the material is subjected to plane stress such that the principal stresses are sigma 1 and sigma 2 is 0.25 sigma 1. Determine the magnitude of sigma 1 that will cause yielding according to maximum distortion energy theory. So let's start with the solution. As we know that we have been given as sigma 1 and sigma 2 which is equal to 0.25 times sigma 1. They are known as principal stresses, and principal stresses are the maximum stresses, maximum or minimum stresses that are acting on this plane state of stress, and we have been given sigma y is equal to 160 megapascal. So according to maximum distortion energy theory, a material will fail when maximum distortion energy, which is sigma 1 square minus sigma 1 into sigma 2 plus sigma 2 square, is equal to sigma yield square. So this is the condition. If this is satisfied, it means that the object will fail or it will start yielding. So you put the value sigma 1 is there, minus sigma 1 and sigma 2 is 0.25 times sigma 1 plus sigma 2 is 0.25 times sigma 1 square is equal to 160 square. Okay, now what we will do is that we will find this sigma 1 square minus this will be 0.25 times sigma 1 square plus 0.25 square will give you 0.0625 times sigma 1 square is equal to 160 square. So 160 square is actually 25600. Okay, now you can see this is plus one value. So if you take sigma 1 square as common from both, it will be 1 minus 0.25 plus 0.0625, and that will be equal to 25600. So I will find 1 minus 0.25 plus 0.0625. That will give you how much? Okay, I have to put the parenthesis at the start. Okay, so this is 0.8125 sigma 1 square is equal to 25600, and this sigma 1 square will be equal to 25600 divided by 0.8125. So I will write 25600 divided by 0.8125, and that will be equal to 31507.69. This is the value of sigma 1, and we know that sigma 1 will be equal to under root 31507.69. And when you take the square root of this value, you will see that you have this sigma 1 which is equal to 177.504 megapascal, and if you round off it, so it will be 178 megapascal. So this is the value of one of the principal stress. Sigma 1 is 178 megapascal that will cause yielding according to maximum distortion energy theory. I hope you have enjoyed this video. Please keep watching and supporting me, and if you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 10-81 that is taken from chapter number 10, Strain Transformation, and book name is Mechanics of Material by R.C. Hibbeler, 9th edition. And the topic that we are covering is theories of failure. So statement is solve problem 10-80 using the maximum shear stress theory. So what is the statement of 10-80? So the yield stress for uranium alloy is 160 megapascal if the machine part is made of this material and critical point in the material is subjected to plane stress such that the principal stresses are sigma 1 and sigma 2 is 0.25 times sigma A. So determine the magnitude of sigma 1 that will cause yielding, and we will using the maximum shear stress theory. So let's start with the solution. As we know that we have been given sigma 1 and sigma 2 is 0.25 times sigma 1. They are principal stresses which are used to apply the failure theory. How we will apply that? We have also given that sigma yield is given as 160 megapascal. So you can see you have both plane stresses sigma 1 and sigma 2. So if you draw the Mohr circle for that you will need two axes. On this x-axis you have normal stresses and on y-axis you have shear stresses. So let this is 1, 2, 3, 4. Let this is sigma 1 and this sigma 2 is this point which is equal to 0.25 times sigma 1 because sigma 1 is greater and sigma 2 is less than this sigma 1. I will put it downward because I have to draw the Mohr circle. So this is the corresponding point. Okay, so what we will do is that if you draw a Mohr circle between sigma 1 and sigma 2, it will be a circle like this. So here this point is sigma 2, this point is sigma 1, and here you know that sigma 3 will be equal to 0. So if you draw a Mohr circle between 2 and 3, and if you draw a Mohr circle between point sigma 1 and sigma 3, so the Mohr circle will be like this one. Okay, now this point is known, at this point we will have maximum shear. How you will find this maximum shear? So this maximum shear stress will be equal to, you can see this is the radius, or this is the radius which is equal to r. Or you can also say that if you take this distance which is from here, this is equal to sigma 1 and this point is equal to sigma 3 which is equal to 0 divided by 2 will give you this radius or this one. Clear? So I can write it sigma 1 minus sigma 3 divided by 2. So sigma 1 is sigma 1 minus 0 divided by 2 will give you sigma 1 divided by 2. So maximum shear stress that we will get is equal to sigma 1 divided by 2. Now from maximum, I will write from maximum shear stress theory, the maximum shear stress is equal to sigma yield divided by 2 for uniaxial tensile test. This is the value of maximum shear stress for uniaxial tensile stress. And you can see that your maximum shear stress, which is this one, this tau max, and that is equal to sigma 1 by 2, will be less than sigma tau max in uniaxial tensile test, which is sigma y divided by 2. But this is the condition for not failure, Okay, so here in this question we have been given that find sigma 1 that will cause yielding. So what we will do, condition, we will write the condition for yielding. Condition for yielding will be your sigma 1 divided by 2 should be greater or equal to this maximum shear stress in tensile test specimen. So for here we will take this condition that sigma 1 over 2 is equal to sigma yield divided by 2. So what we will do is that we will get sigma yield divided by 2 is equal to how much? This sigma y is how much? Sigma y is 160. So 160 divided by 2 is equal to 80. So from here we will get sigma 1 is again equal to 80 multiplied by 2, and that will give you sigma 1 is equal to 160 megapascal. So we have seen that using maximum shear stress criteria, one of the principal stress sigma 1 is 160 megapascal that will cause yielding in the specimen of uranium alloy. And this was all about this problem 10-81. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 10-82 that is taken from chapter number 10, Strain Transformation, and book name is Mechanics of Material by R.C. Hibbeler, 9th edition. And the topic that we are covering is theories of failure. So statement is the state of stress acting at a critical point on seat frame of an automobile during a crash is shown in figure. Determine the smallest yield stress for steel that can be selected for the member based on maximum shear stress theory. So you can see this is the state of element or state of stress on the seat of a crash of automobile. The state of stress is shown over here in this figure. So you have to determine the smallest yield stress for the steel. So let's start with the solution. As we have been given this state of stress, I will draw it a bigger over here. So this is the state of stress here. This is 80 ksi, clear, and the shear stress is how much? 25 ksi. Okay. So if I draw this axis as x-axis and this as y-axis, so you can see this axis is perpendicular to this plane. So this plane is perpendicular to x-axis. So we will take this as sigma x. So here we have sigma x is 80 ksi. Also, you can see on y-axis there is no stress, so sigma y is 0 ksi, and we have tau of xy, which is equal to plus 25 ksi. Why it is tau of xy? Because you can see this plane is perpendicular to x-axis and the shear stress acting on it is tau of x in the direction of y. X represent plane or which this shear stress act, and y in positive direction. So that's why this is positive. Now we have all these values. So what we will do is that we will find in plane principal stresses, or you can also say that we will find principal stresses. And how we'll find this principal stresses? So we know that principal stress sigma 1 comma 2 is equal to sigma x plus sigma y divided by 2 plus minus sigma x minus sigma y divided by 2 whole square plus tau of xy whole square. So just put the value. Sigma x is 80 plus 0 divided by 2 plus minus 80 minus 0 divided by 2 whole square plus tau of xy is 25 whole square under the root. Okay, so sigma 1 comma 2 is 80 divided by 2 plus minus under root 80 divided by 2 whole square plus 25 whole square. Now with the help of calculator, we will calculate the term in the square root. So 80 divided by 2 whole square plus 25 whole square under the root will give you the value, which is 47.169. Okay, now from here we will get sigma 1 is equal to 40 plus 47.169, and sigma 2 will be equal to 40 minus 47.169. So 40, this will be equal to 87.169 unit is ksi. This is sigma 1, and sigma 2 is equal to 40 minus, so it will be minus 7.169 ksi. Now you can see both sigma 1 and sigma 2 have opposite signs. So what we will do, we know that according to maximum, I will write maximum shear stress theory, we have maximum shear stress is sigma 1 minus sigma 2 mod is equal to sigma yield. So this is the condition for failure, for yielding or for failure. For yielding, this is the condition. I will show you here also if you want to draw the Mohr circle for this. So I will take two axes. On x-axis you have normal stress, and in y-axis you have shear stress. So sigma 1 is positive. Let's say this is sigma 1, which is equal to 87.169 ksi, and sigma 2 is minus, which is, for example, this is sigma 2. So sigma 2 is minus 7.169. So if you draw the Mohr circle between these 2 points, so I will roughly draw it, so it will be like this. Clear? This will be the Mohr circle. Now here sigma 3 is equal to 0. So if you draw the Mohr circle between 2 and 3, it will be like this, and from 1 and 3, the Mohr circle will be like this one. Okay. Now the maximum shear stress will be this one. This is the maximum shear stress which is required. We have to find. This is the maximum shear stress due to this loading, and this maximum shear stress is equal to this sigma 1 minus sigma 2, sigma 1 minus sigma 2 divided by 2. Clear? So sigma 1 minus sigma 2 will give you how much? Sigma 1 is 87.169 minus 7.169 divided by 2. So I will get 87.169 plus 7.169 divided by 2 will give you 47.169. This is the value of maximum shear stress due to loading. And we know that maximum shear stress is equal to sigma y divided by 2 for uniaxial tension test. And your this maximum shear stress, which is tau max, I will write it here. This is sigma 1 minus sigma 2 divided by 2 should be, for failure, it should be equal to sigma maximum shear stress in uniaxial tension test, which is sigma y divided by 2. I will write it is, this is also maximum shear stress. Okay, so you can, the 2 will cancel, so we will have sigma 1 minus sigma 2 will be equal to sigma yield, which is written over here. Okay, now sigma 1 is 87.169 minus 7.169 is equal to sigma yield, which is how much, which we are going to find. Sorry, sigma y is we have to find. Okay, so 87.169 plus 7.169 will give you 94. So sigma y is 94.3 KSI. So this is the yield stress of the material that is obtained from this state of stress that is shown in the figure. And I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 10-83 that is taken from chapter number 10, Strain Transformation, and book name is Mechanics of Material by R.C. Hibbeler, 9th edition. And the topic is Theories of Failure. So statement is solve problem 8-10-82 using maximum distortion energy theory. In our previous problem that we have done 10-82 using maximum shear stress theory, so we will solve the same problem by using maximum distortion energy theory. So statement is the state of stress acting at a critical point on seat frame of an automobile during a crash is shown in figure. Determine the smallest yield stress for steel that can be selected for the member, and that is based on maximum distortion energy theory. So you can see this is the element and the state of stress is shown over here, clear, and you have to find the minimum yield stress for the material. So let's start with the solution. The first step is that I will draw this member a little bit bigger so that you have a clear understanding. This is 80 KSI and this shear stress is 25 KSI. So from here, if you take this axis as x-axis and this as y-axis, so you can see this plane, this axis is perpendicular to this plane, so this will be x plane and the direction is in x direction, so this will be sigma x. So we will write sigma x here is equal to 80 KSI. Now you can see on this plane is perpendicular to y-axis and there is no stress that is perpendicular to it, so we have sigma y is equal to 0. Now we have another shear stress which we can write as tau of xy, that is 25 KSI plus 25 KSI. How? You can see this x plane which is perpendicular to this x-axis and this shear stress acting is tau of, because this is acting in x plane and y is the direction in which this stress is applied and this is in positive direction, so it will be plus 25 KSI. Now what we will do is that for using maximum distortion energy, for maximum distortion energy theory, for plane state of stress problem, we have this condition for failure or yielding, that sigma 1 square plus sigma 2 square minus sigma 1 into sigma 2 should be equal to sigma yield square. This is the condition. So for that we will find sigma 1 and sigma 2. They are called principal stresses. So we will find this principal stresses from this state of stress. So how we will find this? Because we know that sigma 1 comma 2 is equal to sigma x plus sigma y divided by 2 plus minus sigma x minus sigma y divided by 2 whole square plus tau of xy square. Okay, we will put the value sigma x is 80 plus 0 divided by 2 plus minus under root 80 minus 0 divided by 2 whole square plus 25 whole square under the root. So sigma 1 comma 2 will be equal to 80 divided by 2 plus minus 80 divided by 2 whole square plus 25 whole square. Okay, so this will give you 40 plus minus the value in the under root. We will calculate it. So 80 divided by 2 whole square plus 25 whole square under the root. This will give you 47.169. So sigma 1 will be equal to 40 plus 47.169 and sigma 2 will be equal to 40 minus 47.169 KSI. So here we will get 87.169 KSI and sigma 2 will be equal to minus 7.169 KSI. Now you have both value of sigma 1 and sigma 2, so put it in this condition in maximum distortion energy theory, or we also see it can write it as distortion energy theory. So that is equal to sigma 1 square minus sigma 1 into sigma 2 plus sigma 2 square is equal to sigma yield square. That is for yielding. And if you do not want yield, so this should be less than sigma yield square. Here we are finding the minimum yielding, so we will take it equal. So now put the value 87.169 square minus 87.169 multiplied by minus sigma 2 is 7.169 plus minus 7.169 whole square is sigma yield square. Okay, so I will move the calculator over there. So I will have 87.169 square minus 87.169 multiply by minus 7.169 plus minus 77.169 whole square, and that will give you 8274.73. that is equal to sigma y square. So sigma yield will be equal to under root 8274.73. So if you take the square root of this answer, so we will get sigma y is equal to 90.965 KSI. So if you round it off, so it will be 90.95 is 91 KSI. So this is the minimum yield stress of the material that can be required for yielding under this state of stress condition. So this was all about this problem 10-83. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.